Hello students, this is Mr. Deaver, and in this video we're going to talk about pH and how we measure acids and bases. Now last week we talked about how acids and bases are very much a part of our world and they're super important. For example, some fruits are mildly acidic, carbon dioxide dissolves in water which creates both carbonated soft drinks and also causes ocean acidification, and often cleaning products contain basic compounds. But what's a situation in which we really care about the pH of something? Let's look at another example. Now, usually our blood is very slightly basic, but sometimes people with diabetes experience a condition that causes very dangerously acidic blood. Perhaps you remember from biology that enzymes are proteins that perform various functions in our body, and insulin is a super important enzyme. Our body, of course, breaks down the food that we eat into glucose, which we then use as a fuel. But insulin does the very important task, performs the very important task of moving that glucose from our blood into muscle cells or nerve cells or whatever tissues in our body need energy. So without that insulin, your body has plenty of glucose in the blood, but it's not able to use that glucose. So blood glucose levels keep getting higher and higher. Meanwhile, your body still doesn't have energy, and your body goes looking for an alternate energy source. Therefore, it starts to break down fat and muscle, which produces something called ketones. Now, ketones are acidic, which starts to make your blood a little bit more acidic. Now, this isn't always a problem. In fact, this process, or some kind of ketosis, may start to happen on a small scale if you go too long without eating, or if you're on a very low carbohydrate diet. But in some people with diabetes, this process can go out of control, and their blood becomes very dangerously acidic. We call this diabetic ketoacidosis. And if a doctor suspects that a patient is experiencing this, he or she may need to do a pH test. Okay, so what exactly is pH? pH is a measure of the concentration of H plus ions or hydronium ions. Okay, this means concentration of H plus. Now remember that H plus doesn't actually exist as a free ion in solutions. Even though we sometimes talk about H plus ions, they're reacting with water to make H3O plus or hydronium. Now, when we write these square brackets here, what that means is concentration. So this means H plus concentration. We also sometimes use POH, which is a measure of the OH minus concentration. Now, come on, really, we can't make this any easier for you. I mean, pH literally has an H in it. So pH is a measure of H plus concentration, and POH literally has the letters OH minus in it. So should be hopefully pretty easy, right? I mean, if you can't get this straight, that's pretty pathetic. Get it? Pathetic, because POH kind of looks like pathetic. Okay, I know. It's not my best work, not my best joke ever. I'll do better next time, okay? I promise. Okay, one more note before we move on to the next slide. When we use concentration in chemistry, how do we measure it? Well, usually we use our old friend molarity. We measure concentration with molarity. Molarity is moles divided by liters. Now, this chart shows us the relationship between H plus concentration, OH minus concentration, pH, and POH among acids, bases, and neutral substances. Let's see if we can use the chart to fill in these blanks, and let's start with acids. So in an acidic solution, we probably already know this, that pH is less than 7. We can see that here. What about our H plus concentration? Let's look at that. Well, you may think that as we get more acidic here, that our H plus concentration is getting smaller because 1 is smaller than 6. But remember, what do these negative exponents mean? So 10 to the 1 is really just 10. 10 to the 0 is really just 1. 10 to the minus 1 is really just 0.1. So 10 to the minus 2 would really be 0.01, and 10 to the minus 3, 0.001. So as we continue moving in this direction and our exponents are getting more and more negative, the numbers are getting smaller. So acids have a H plus concentration of greater than 10 to the negative 7. And that makes sense because acids should have a high H plus concentration, right? We know that acids dissociate in water to make an H plus ion and also an anion. So even though, even though 0.1 is a pretty small number, it's a lot bigger than these numbers down here. And a 0.1 molar acid is actually a really strong acid. Okay, what about pOH? Okay, we can see here that acids are going to have a pOH of greater than 7, and their OH concentration is getting smaller than 10 to the minus 7. So just a couple of the things I want you to notice here. Notice that as pH is going up, pOH is going down. So pH and pOH are inversely related. As one increases, the other decreases. Now, pH and H plus concentration are obviously connected because it's right there in the words. Okay, so we know that acids have a low pH and a high H plus concentration. What about H plus concentration and OH minus concentration? I also want you to notice that they are inversely related. So as we increase our H plus concentration, our OH minus concentration is getting smaller. As one goes up, the other goes down, always. I want to show you that with a quick animation here. So notice that in this animation, this here tells us our H plus concentration, this here tells us our OH minus concentration, and that tells us our pH. Now with water, right now we have water in this container. Our pH is 7, and our H plus concentration and OH minus concentration are the same. But let's fill this container with something really acidic. Let's say battery acid, okay? So notice that our H plus concentration just shot way up, and our OH concentration shot way down. As one goes up, the other goes down. Now, if I start to put water in here and dilute the solution, what do you think is going to happen? Well, notice that as we put water in here, our H plus concentration is going a little bit down, and our OH minus concentration is going a little bit up. So I can add some more water here. I'm going to empty out my container a bit, add some more water to keep diluting it, and the same thing's going to happen. As one goes up, the other goes down. They're inversely related. All right, now I want you to pause the video and fill in the rest of these blanks on your own, and then come back when you're ready. Okay, we're back. So for a neutral substance, like we saw in the animation, pH and pOH are both the same, and they're both exactly 7. H plus concentration and OH minus concentration, both exactly the same, and they're both exactly 10 to the negative 7. Now, with bases, if we look back at our chart, with bases, they have a high pH above 7 and a low pOH below 7. What about our H plus concentration and our OH minus concentration? Bases are going to have a very low H plus concentration and a very high OH minus concentration. So that H plus concentration less than 10 to the negative 7 and OH minus concentration is greater than 10 to the negative 7. Now this makes sense because we know from last week that most bases dissolve and dissociate in water to create hydroxide ions. So of course bases are going to have a greater concentration of hydroxide. Notice also that acids and bases are the complete opposite in all 4 of these measures. Okay, now we've seen that this relationship between H plus concentration and OH minus concentration is an inverse relationship. As one goes up, the other goes down. But why is this? Well, the reason is because occasionally water molecules collide and undergo something called self-ionization. And what happens in self-ionization is that these two water molecules collide, and one of the H's one of the water molecules donates an H plus ion to the other water molecule. So this H plus ion gets transferred, which makes H3O plus and OH minus. So in a way, water is actually the perfect molecule for social distancing because it doesn't need anybody else. It can react with itself just fine, all while staying 6 feet away from other molecules. But keep in mind that this doesn't happen that much in water. It happens only to a very small extent, and to a small extent. So in a container, in a big container of water, or in any container of water, there's only going to be a few H3O plus and OH minus molecules. Regardless of how many there are, though, in pure water, there has to be the exact same number. In pure water, the same number of H3O plus and OH minus ions, because in this reaction, we get exactly one of each. So that explains why pure water has a pH of 7 and why pure water has equal concentrations of H3O plus and OH minus, because if we make one, we have to make another with this reaction. Also, remember that water is an amphoteric molecule because it can act as both an acid and a base. So one of these water molecules is going to donate an H+, which means it's acting as an acid. The other one accepts an H+, which means it's acting as a base. And of course, on the other side, we have a conjugate acid and base because this reaction is reversible. So H3O plus can donate that proton right back, which means that this would act as an acid. Now, just a few weeks ago, you learned about equilibrium and Le Chatelier's principle, and what happens if we put stress on a system at equilibrium by adding reactants or products. Keep that in mind as we answer these next two questions here. Let's say that we add H plus ions to a system by, say, dissolving an acid in water. How is that going to affect our system? Well, let's look at our equation here. If we add H plus ions to the system, now there's going to be too many products on this side, and it's going to increase the reaction happening to the left. If the reaction to the left is happening more, that's going to use up some of this OH, and the concentration of OH is going to decrease. So again, notice what happened here. We increased H plus ions, we added H plus ions, OH minus decreases. The concentration of OH minus decreases. If one goes up, the other goes down. Let's look at it visually real quick here. Now, right here, our system is at equilibrium. And we can see the concentration of H plus, OH minus, and H2O. Now, here, when we add H plus, now there's going to be a lot more things on this side of our equation. There's going to be a lot more reactants in this case. And the reaction in this direction is going to start happening more. So our concentration of water is definitely going to increase because more water is going to be produced. And the concentration of both H plus and OH minus are going to decrease from the time when we added H plus. But notice that our concentration of H plus is still higher here than it was before we added any. So since H plus concentration is going from here to here, it is increasing. What about the OH minus concentration? It went from here down to here. It decreased. So again, notice as one goes up, the other goes down. Now, since H plus concentration actually increased, what does that mean for our pH? Well, if H plus concentration is higher, that means the substance is more acidic, which means pH is lower. Okay, one more thing. Let's look at if we add OH minus or hydroxide ions by, say, dissolving a base in water. Well, now we're going to have a lot more hydroxide ions, a lot more things on this side of our equation. And that extra OH that we added is going to react with H+. So the reaction happening this way to the left is going to happen more. So if this reaction to the left is happening more, what's going to happen to our H plus concentration? It's going to decrease. Remember, we added OH minus. We increase that. H plus has to decrease. As one goes up, the other goes down. That's an inverse relationship. Okay, I hope this video was helpful. Now, there is a reading and some summary questions for you to answer on your practice worksheet.